Chapter 10. Engineering Data.
Next, we turn to valve materials.
In this chapter, I would like to introduce the engineering data section covering the standard specifications of materials used in control valves. Each material is organized by a material code number and is cross-referenced with the table that follows. The first material code, number 1, is cast carbon steel, ASTM A216 grade WCC. The usable temperature range is from -20 degrees Fahrenheit to 800 degrees Fahrenheit, or -29 degrees Celsius to 427 degrees Celsius. Its composition consists of a maximum of 0.25% carbon, 1.2% manganese, 0.04% phosphorus, 0.045% sulfur, and 0.6% silicon. Material code 2 is also cast carbon steel, ASTM A352 grade LCC. It is used for low temperatures, ranging from -50 degrees Fahrenheit to 650 degrees Fahrenheit, or -46 degrees Celsius to 343 degrees Celsius. The composition is the same as the WCC mentioned previously. Next, we move on to Material Code 3 carbon steel bar stock.
Material Code 3 is carbon steel bar stock, AISI 1118, UNSG 10180. The operating temperature is the same as the cast steel mentioned before, from -20 degrees Fahrenheit to 800 degrees Fahrenheit, or -29 degrees Celsius to 427 degrees Celsius. Looking at the composition, carbon is between 0.15% and 0.2%, manganese is between 0.6% and 0.9%, phosphorus is a maximum of 0.04%, and sulfur is a maximum of 0.05%. A characteristic of the bar stock specification is that the carbon content is designated as a clear range. Material Code 4, leaded steel bar stock, follows immediately.
Material Code 4 is leaded steel bar stock, AISI 12L14, UNSG 12144. The operating temperature range is -20 degrees Fahrenheit to 800 degrees Fahrenheit, or -29 degrees Celsius to 427 degrees Celsius. The composition includes a maximum of 0.15% carbon and 0.85% to 1.15% manganese. Notably, phosphorus is set higher than general steel at 0.04% to 0.09%, and sulfur is at 0.26% to 0.35%. Additionally, 0.15% to 0.35% lead is added. This combination of sulfur and lead significantly improves machinability, creating the characteristics of free-cutting steel.
Here, I would like to introduce 4 types of chrome-moly and nickel steels. Material Code 5 is AISI 4140 chrome-molybdenum steel, which is similar to ASTM, a 193 grade B7 bolt material. The operating temperature is -55 degrees Fahrenheit to 1000 degrees Fahrenheit, or -48 degrees Celsius to 538 degrees Celsius, with 0.38% to 0.43% carbon, 0.8% to 1.1% chromium, 0.15% to 0.25% molybdenum, and the remainder is iron. Material Code 6 is forged 3.5% nickel steel, ASTM A352 grade LC3. Since it is for low temperatures, it is used from -150 degrees Fahrenheit to 650 degrees Fahrenheit, or -101 degrees Celsius to 343 degrees Celsius, and contains 3% to 4% nickel. Material Codes 7 and 8 are cast chrome-molybdenum steels, both ASTM A217. WC6 contains 1% to 1.5% chromium and 0.45% to 0.65% molybdenum, while WC9 has higher contents with 2% to 2.75% chromium and 0.9% to 1.2% molybdenum. Both materials withstand high temperatures from -20 degrees Fahrenheit up to 1,100 degrees Fahrenheit, or -29 degrees Celsius to 593 degrees Celsius. It is helpful to remember that chromium and molybdenum content is increased to handle higher temperatures.
Now we move on to high-temperature chrome-molybdenum steel and the stainless steel series. Material code 9 is forged chrome-molybdenum steel, ASTM A182 grade F22, used from -20 degrees Fahrenheit to 1100 degrees Fahrenheit, or -29 degrees Celsius to 593 degrees Celsius, with 2% to 2.5% chromium and 0.87% to 1.13% molybdenum. Material code 10 is cast chrome-molybdenum steel, ASTM A217 grade C5. By significantly increasing the chromium content to 4% to 6.5%, it withstands even higher temperatures from -20 degrees Fahrenheit to 1200 degrees Fahrenheit, or -29 degrees Celsius to 649 degrees Celsius. Material code 11 is Type 302 stainless steel, ASTM A479 grade UNS S30200, which has a wide range from -325 degrees Fahrenheit to 1500 degrees Fahrenheit, or -198 degrees Celsius to 816 degrees Celsius, with 17% to 19% chromium and 8% to 10% nickel. Material code 12 is Type 304L stainless steel, ASTM A479 grade UNS S30403, which is a low-carbon type with carbon reduced to a maximum of 0.03%. It contains 18% to 20% chromium and 8% to 12% nickel, and can be used from cryogenic temperatures of -425 degrees Fahrenheit -254 degrees Celsius up to 800 degrees Fahrenheit 427 degrees Celsius.
Finally, I would like to introduce cast type 304L, 316L, and 316 stainless steels. Material code 13 is cast type 304L stainless steel, ASTM A351 grade CF3, used from -425 degrees Fahrenheit to 800 degrees Fahrenheit, or -254 degrees Celsius to 427 degrees Celsius. It has a maximum of 0.03% carbon, 18% to 21% chromium, 8% to 11% nickel, and a maximum of 0.5% molybdenum. Material code 14 is Type 316L stainless steel, ASTM A479 grade UNS S31603, used from -425 degrees Fahrenheit to 850 degrees Fahrenheit, or -254 degrees Celsius to 454 degrees Celsius. This is a low-carbon type with carbon reduced to 0.03%, containing 16% to 18% chromium, 10% to 14% nickel, 2% to 3% molybdenum, a maximum of 0.1% nitrogen, and the remainder is iron. The characteristic of the 316 series is the addition of molybdenum to increase corrosion resistance. Material code 15 is Type 316 stainless steel, ASTM A479 grade UNS S31600, used widely from -325 degrees Fahrenheit to 1500 degrees Fahrenheit, or -198 degrees Celsius to 816 degrees Celsius. However, for high temperatures exceeding 1000 degrees Fahrenheit 538 degrees Celsius, there is a condition that carbon must be 0.04% or higher.
Now, I would like to introduce the composition of Type 316 forged stainless steel, followed by the cast Type 316, also known as CF8M. The composition of forged Type 316 is 0.08% carbon max, 2% manganese max, 0.045% phosphorus max, 0.03% sulfur max, and 1% silicon max. Looking at the key alloying elements, chromium is 16.0 to 18.0%, nickel is 10.0 to 14.0%, and molybdenum is 2.0 to 3.0%, with nitrogen at 0.1% max, and the remainder being iron. A key characteristic of Type 316 is that the addition of molybdenum further enhances resistance to pitting and crevice corrosion. Next, material number 16 is cast Type 316, specified as ASTM A351 grade CF8M. The operating temperature range is very wide, from -425 to 1500 degrees Fahrenheit, which is -254 to 816 degrees Celsius. However, please keep in mind that when used above 1000 degrees Fahrenheit, or 538 degrees Celsius, There is a separate requirement for a carbon content of 0.04% or higher.
I will now introduce the detailed composition of the CF8M cast material mentioned earlier, followed by type 317 forged stainless steel. The composition of CF8M, which is cast type 316, is 0.08% carbon max, 1.5% manganese max, 1.5% silicon max, and 0.04% max for both phosphorus and sulfur. The alloying elements are 18.0 to 21.0% chromium, 9.0 to 12.0% nickel, and 2.0 to 3.0% molybdenum. Compared to the forged material, the chromium range is slightly higher. Next, material number 17 is type 317 stainless steel, specified as ASTM 479 grade UNSS 31700. The operating temperature range is minus 325 to 1,500 degrees Fahrenheit, or minus 198 to 816 degrees Celsius. Similarly, if used above 1,000 degrees Fahrenheit or 538 degrees Celsius, the condition of 0.04% carbon or higher applies. The key point is that type 317 is a grade where corrosion resistance is further strengthened by increasing the molybdenum content compared to type 316.
I would like to introduce the detailed composition of type 317 and its cast form CG8M. The composition of forged type 317 is 0.08% carbon max, 2% manganese max, 0.045% phosphorus max, 0.03% sulfur max, and 1% silicon max. The alloying elements are 18.0 to 20.0% chromium, 11.0 to 15.0% nickel, and 3.0 to 4.0% molybdenum, which is significantly higher than the 316 series. Nitrogen is 0.1% max and the remainder is iron. Following this, material number 18 is cast type 317, specified as ASTM A351 grade CG8M. The operating temperature range is minus 325 to 1,000 degrees Fahrenheit, or minus 198 to 538 degrees Celsius, which has a lower upper limit than the forged material. The composition of CG8M is 0.08% carbon max, 1.5% manganese max, 1.5% silicon max, 0.04% max for both phosphorus and sulfur, 18.0 to 21.0% chromium, 9.0 to 13.0% nickel, and 2.0 to 3.0% molybdenum.
Now I will introduce type 410, which is martensitic, and 17-4pH, which is a precipitation hardening steel. Material number 19, type 410, is specified as ASTM A276 grade S41000, and its operating temperature is divided into two based on the heat treatment condition. In the annealed condition, it is minus 20 to 1,200 degrees Fahrenheit, or minus 29 to 649 degrees Celsius. When heat treated to 38 HRC, it is minus 20 to 800 degrees Fahrenheit, or minus 29 to 427 degrees Celsius. The composition is 0.15% carbon max, 11.5 to 13.5% chromium, 1% manganese max, and the remainder is iron. Material number 20, type 17-4pH, is ASTM A564 grade 630, UNS S17400. The basic operating temperature is minus 20 to 650 degrees Fahrenheit, or minus 29 to 343 degrees Celsius, but for applications such as cages where stresses are generally compressive and there is no impact loading, it can be used up to 800 degrees Fahrenheit, or 427 degrees Celsius. The composition is 15.0 to 17.5% chromium, 3.0 to 5.0% nickel, 3.0 to 5.0% copper, 0.15 to 0.45% niobium, and 0.07% carbon max.
I will now introduce the high alloy series, 254 SMO super austenitic steel and 2205 duplex steel. Material number 21, type 254 SMO, is specified as ASTM A479 UNS S31254, with an operating temperature of minus 325 to 750 degrees Fahrenheit, or minus 198 to 399 degrees Celsius. Its composition includes 18.5 to 20.5% chromium, 17.5 to 18.5% nickel, 6.0 to 6.5% molybdenum, and 0.18 to 0.22% nitrogen. The very high molybdenum and nitrogen content provide excellent pitting resistance. Carbon is 0.02%. Max material number 22 is its cast form, ASTM A351CK3MCUN, with 19.5 to 20.5% chromium, 17.5 to 19.5% nickel, and 6.0 to 7.0% molybdenum. Material number 23, type 2205, is a duplex stainless steel specified as ASTM A279US S31803, with an operating temperature of minus 20 to 600 degrees Fahrenheit, or minus 29 to 316 degrees Celsius. The composition is 21.0 to 23.0% chromium, 4.5 to 6.5% nickel, 2.5 to 3.5% molybdenum, and 0.03 to 0.2% nitrogen. Finally, material number 24 is its cast form, ASTM A890 grade 4A, also known as CD3MN.
I will introduce the cast 2205 duplex stainless steel and cast iron materials. Material code 24 is cast type 2205 S31803 steel, specified as ASTM 890 grade 4A CD3MN. The operating temperature range is minus 20 to 600 degrees Fahrenheit, which is minus 29 to 316 degrees Celsius. The composition is 0.03% carbon max, 1.5% manganese max, 1% silicon max, 0.04% phosphorus max, 0.02% sulfur max, and, as alloying elements, 21 to 23.5% chromium, 4.5 to 6.5% nickel, 2.5 to 3.5% molybdenum, 0.1 to 0.3% nitrogen, and the remainder is iron. Material code 25 is cast iron, specified as ASTM A126 Class B, UNS F12102. For pressure-retaining components, it is used from minus 20 to 450 degrees Fahrenheit, or minus 29 to 232 degrees Celsius. And for non-pressure-retaining components, it can be used from minus 100 to 800 degrees Fahrenheit.
I would like to introduce the low-temperature use caveats for cast iron and Class C cast iron. According to the ANSI B31.5 standard, if the maximum stress does not exceed 40% of the ambient allowable stress, it can be applied down to minus 150 degrees Fahrenheit minus 101 degrees Celsius. In other words, if there is sufficient stress margin, the low-temperature usage limit can be lowered. The composition of Class B cast iron is 0.75% max phosphorus and 0.15% max sulfur. Next, material code 26 cast iron is ASTM A126 Class C, UNS F12802. Pressure-retaining components are used from minus 20 to 450 degrees Fahrenheit, minus 29 to 232 degrees Celsius, and non-pressure retaining components are used from minus 100 to 800 degrees Fahrenheit.
I would like to introduce ductile iron, ductile and iron-resist iron, and valve bronze. The same caveat applies to the previously mentioned Class C cast iron. Per ANSI B31.5, if the maximum stress is 40% or less of the allowable stress, it can be used down to minus 150 degrees Fahrenheit, with phosphorus at 0.75% max and sulfur at 0.15% max. Material code 27, ductile iron, is ASTM A395 type 60-40-18, where these numbers represent a tensile strength of 60 ksi, a yield strength of 40 ksi, and an elongation of 18%. The operating temperature is minus 20 to 650 degrees Fahrenheit, minus 29 to 343 degrees Celsius. And the composition is 3% min carbon, 2.5% max silicon, and 0.08% max phosphorus. Material code 28, ductile and iron-resist iron, is ASTM A439 Type D2B, UNS F43001, and it withstands temperatures from -20 to 1,400 degrees Fahrenheit, -29 to 760 degrees Celsius. This composition is 3% min carbon, 1.5 to 3.0% silicon, 0.70 to 1.25% manganese, 0.08% max phosphorus, 18 to 22% nickel, and 2.75 to 4.0% chromium. It is characterized by its high nickel content, making it strong against high temperatures and corrosion environments. Next, material code 29 is valve bronze.
I would like to introduce the bronze series materials, which are copper-based alloys. Material code 29, valve bronze, is ASTM B61, UNS C92200, with an operating temperature from -325 to 550 degrees Fahrenheit, -198 to 288 degrees Celsius. The composition is 86 to 90% copper, 5.5 to 6.5% tin, 1 to 2.0% lead, and 3.0 to 5.0% zinc. Material code 30, tin bronze, is ASTM B564 grade C9500, ranging from -325 to 400 degrees Fahrenheit, with 86 to 89% copper and 9.0 to 11.0% tin, meaning it has a higher tin content. Material code 31, manganese bronze, is ASTM B584 grade C86500, ranging from -325 to 350 degrees Fahrenheit, and is characterized by 55 to 60% copper, 36 to 42% zinc, and 0.4 to 2.0% iron. Material code 32, cast aluminum bronze, is ASTM B148 grade C95400, with 83% min copper, 10 to 11.5% aluminum, and 3.0 to 5.0% iron. The temperature range is -325 to 500 degrees Fahrenheit based on B31.1 and B31.3, and it extends up to 600 degrees Fahrenheit based on ASME Section 8.
I would like to introduce additional aluminum bronze, brass, naval brass, and aluminum bar stock. Material code 33, cast aluminum bronze, is ASTM B148 grade C95800, ranging from -325 to 500 degrees Fahrenheit, with 79% min copper, 8.5 to 9.5% aluminum, 3.5 to 4.5% iron, and 4.0 to 5.0% nickel, containing more nickel than the previous C95400. Material code 34, B16 yellow brass bar, is ASTM B16 grade C36000 in a half-hard state, and is used for non-pressure retaining components from -325 to 400 degrees Fahrenheit. The composition is 60 to 63% copper, 2.5 to 3.7% lead, and the remainder is zinc. Material code 35, naval brass forgings, is ASTM B283 alloy C46400, ranging from -325 to 400 degrees Fahrenheit, and is characterized by 59 to 62% copper and 0.5 to 1% tin. Material code 36, aluminum bar stock, is ASTM B211 alloy A96061 T6 and can be applied to cryogenic temperatures from -452 to 400 degrees Fahrenheit, -269 to 204 degrees Celsius. It contains 0.8 to 1.2% magnesium, 0.4 to 0.8% silicon, 0.15 to 0.4% copper, 0.04 to 0.35% chromium, and the remainder is aluminum.
I would like to introduce cobalt-based alloys in nickel alloy series. Material code 37, cobalt-based alloy 6, is provided as cast UNS R30006 or weld filler co-CRA, with an operating temperature from -325 to 1,500 degrees Fahrenheit, -198 to 816 degrees Celsius. It contains 0.9 to 1.4% carbon, 3.0 to 6.0% tungsten, and 26 to 32% chromium, with the remainder being cobalt. It is a wear-resistant alloy for hard-facing. Material code 38 NICU alloy bar K500 is B865 grade N05500, ranging from -325 to 900 degrees Fahrenheit, and is a precipitation-hardened alloy containing 63 to 70% nickel, 2.3 to 3.15% aluminum, 0.35 to 0.85% titanium, and the remainder copper. Material code 39 cast NICU alloy 400 is ASTM A494 grade M35-1, and within the same temperature range it contains 26 to 33% copper and the remainder nickel. Material code 40 NIRMO alloy C276 bar is ASTM B574 grade N10276, a high corrosion-resistant alloy that withstands -325 to 1,250 degrees Fahrenheit, -198 to 677 degrees Celsius, which leads into material code 41, NIRMO alloy C.
In this chunk, I would like to introduce nickel-chromium-molybdenum alloy C276, which is item 40 among the valve material specifications. The specification is ASTM B574 grade N1276, and it is in the form of bar stock. Looking at the chemical composition, chromium is 14.5 to 16.5%, and molybdenum is 15.0 to 17.0%. With these key elements for corrosion resistance present in high amounts. Iron is 4.0 to 7.0%, tungsten is 3.0 to 4.5%, and cobalt is a maximum of 2.5%. It is an ultra-low carbon material with carbon at a maximum of 0.01% and silicon at a maximum of 0.08%, while manganese is a maximum of 1% and vanadium is a maximum of 0.35%. Phosphorus is 0.04, sulfur is 0.03, and nickel fills the remainder as the balance element. This alloy has a wide temperature range, as it can be used from -325 to 1,250 degrees Fahrenheit, which converts to -198 to 677 degrees Celsius.
Next, I will introduce the nickel-chromium-molybdenum alloy C, casting specification ASTM A494CW20M. The operating temperature range for this material is -325 to 1,000 degrees Fahrenheit, or -198 to 538 degrees Celsius. Regarding the composition, chromium is 15.5 to 17.5% and molybdenum is 15.0 to 17.5%, with these two elements being the primary components for corrosion resistance. Iron is limited to 2% or less, and tungsten is limited to 1% or less. Trace elements include carbon at 0.02% or less, silicon at 0.8% or less, and manganese at 1% or less, while phosphorus is 0.03, sulfur is 0.03, and the rest is filled with nickel. This alloy is a nickel-based high-corrosion-resistant alloy used for valve components in environments that are highly corrosive or high temperature. With this item, we conclude this section, and next, we will see a table summarizing the mechanical and physical properties of valve materials used for pressure-containing components. Please remember that the material code numbers in this table correspond exactly to the numbers in the previous standard specifications for valve materials list.